Alrighty, so here we have the second kinetics quiz for Engineering 2030. One question only, but here is my explanation, sorry. We have, we're going to use kinetics, F equals ma. We have a car stops over a distance of 44.3 meters from an initial velocity of 11.4 meters per second. We then, our objective is to calculate the braking distance of how long it would, or calculate how long it would take the car to brake when it is going up a 7.1 degree incline, 1 decimal place of accuracy. So, first step, we don't even want to worry about that part yet. We want to focus on the acceleration from the initial given conditions, because it's on flat land. So here we have a diagram. Here's our car, initial velocity going that way. Our acceleration is going to be that way. So that means our net forces are going to be that way. Here's our free body diagram, as well as our kind of kinetic diagram as well. 2 different colors just to kind of relate things. I'd also put that we want acceleration that way. Positive. So here our objective is to find the acceleration of it, and we'll find the acceleration and then use that acceleration that we find to determine our braking force. So you can see here we don't have any, we have 2 forces for the y directions, and that means that they equal each other, that the normal force is equal to the weight, but we have no mention of friction, just braking distance. So I'm assuming that the only force going the other way is brake, or is the force of the brakes, no friction. So find the acceleration. We can use this kinematic equation here. Initially I was like, oh, it should be easy, but we don't have the time it takes, so cross that out. But we have the final velocity, we have the initial velocity, and we have the distance traveled, and a constant. So that leaves the acceleration as the only unknown. Do some algebra, goes to 0, move some things around, move some more things around, and we get that acceleration for the given conditions as negative 1.47 meters per second squared. Still very far away from our final goal. Just checking the work, making sure everything cancels out. And then this is where we start using kinetics. So we know that the sum of forces is equal to the mass times acceleration. I guess this could potentially be tangent. It's just going in a straight direction. There's no, radial forces and such, or acceleration. So here we have, using our free body diagram, for, again, no acceleration in the y direction, so those kind of go away, or we just don't need them. And then our one force in the x directions is just the braking force. So we are not given a mass of the car, but that's okay, as you'll see later on. So that doesn't really matter. We plug in our known acceleration, and our braking force is in the negative direction, so we know that the force of braking is equal to 1.47 times the mass of the car. We'll use that later on. Coming up next, we have the actual incline, and so we know it's 7.1 degrees, as you can see there. Then our free body diagram here, we have the weight, and then we have the normal force, and then we still have the braking force. Again, no signs of friction unless you count the braking force as that. But then our kinetic part of the diagram, velocity going up it, and then our acceleration being in that direction, And then the easiest way to do this is just redefine how you define x and y. So positive going that way for x, positive going that way for y. So we know that, again, nothing is happening in the y direction. It is all, we are accelerating that way, but moving that way up the slope. So the f of y, we know the acceleration is equal to 0, as I have there. That means that the normal force is equal to the weight in the y direction. Again, this doesn't really matter actually because we don't have any friction, so normal force doesn't really matter, but normal force is equal to the mass of the car times gravity times cosine of 7.1 degrees. Then in our x direction, which is where we're finding our distance traveled, we have the sum of forces in the x direction is equal to the mass times the acceleration in the x direction. And this is, we are looking for the acceleration here. That's our big component. And so we have the force of the brake minus the weight in the x direction is equal to the mass times the acceleration in the x direction. So we know the force of the brake is equal to negative 1.47 times the mass of the car. And then we know that the weight is equal to the mass of the car times gravity times sine times 7.1 degrees, or sine of 7.1 degrees. And we know from the free body diagram that it is going, that is going that way. So that's Wx. And then that's equal to the mass of the car times the acceleration in the x direction. And guess what? Mass of the car cancels. So that does not matter to us. So, which is good because it is not given. And so doing some algebra, we actually don't have to move everything. We can just plug in gravity. And we know minus negative 1.47 minus 9 times 9.81 times sine of 7.1 is equal to negative 2.679 meters per second squared. And so we can use our equation from earlier again. Again, we know that the final velocity is equal to 0. Again, this is all velocities. The x direction, I guess we could point that equals 11.4 meters per second. And we are looking for how far up the hill it goes. So again, final velocity equals 0. Negative v of 0 squared over 2a is equal to delta x, that's our equation after a bit of algebra, the same equation we used earlier. Then we get delta x is equal to 24.25 meters, or using significant figures, 24.3 meters. And to check it, this is way less than the initial. I mean, if you look at our accelerations, given that we have gravity working against it as well, even though it's only a very small bit of gravity, because the 7.1 is just slightly uphill, it does add quite a bit, because, I mean, our initial is just from the braking force, and you're pretty much doubling the amount of force on it going in the negative direction. So, given the initial one was 44.3 meters, about half of that makes sense to me.